Yo, I can't hear you, Professor.
Can you hear me now?
Yeah.
Yes.
Okay. Yeah, I was just giving out the answer to the final exam. I'm sure you all heard that.
Very funny.
I-
Can you repeat that one more time?
well, actually, I mean, I have like many exams posted, but let's talk about. So let's talk about midterm two. People did fairly well. I've only graded 15 so far. Um, but I thought I'd just give some feedback and some thoughts. Okay. So for the DF2 problem, people are really getting it. Um, Things that they used to make mistakes with, they're not making this semester. The mistakes there are, it's all in the B summer, either not connecting something or shorting something. Now the gain bandwidth problem, there's like some confusion where the first step is to put it into the Q of S type form, and H of S is just the op amp itself without the feedback network, right? So what some people are doing are just trying to perform, is it over under critically damped on H of S rather than the whole thing. Sometimes they get that right, but they're mistaking beta for for the actual gain rather than one over the gain. And so that throws off the answer. But then people are mistaking um, this bit here. So when you're supposed to find that equation, right? Find the relationship that makes that a non-inverting op amp. Well, you have the old numerator part, right? That has to be much less than beta open loop gain. And if you look at the question, you can see what we're saying, but somewhere that's got to be said. Just writing out QS properly is not enough. Unfortunately, there's a lot of, for those that are not getting it right, sometimes it's just being lost. And it'll take more analysis to figure out how to bring you back. Um, the spring mass damper RLC, people are really getting all of that correct. Although if you do get the wrong schematic, right, the rest of it's going to be wrong because, um, people might be putting down the schematic that they know the answer to rather than the one that's there. Um, actually, but that being said, I don't see a lot of people being lost. Now in the control, there is some confusion about what it means to identify the reason for being out of control, right? Saying, kind of using the shorthand of Descartes' rule, saying something's missing or something's negative isn't really enough. Now, I let it go this time, probably because I have old exam solutions out there, or maybe I didn't cover it enough. But really, the way to answer that part is you use a quadratic equation to find the poles, right? And if the real is equal to 0, right, it's an integrator, right? If it's imaginary only imaginary, it's an oscillator, right? And then anything real on the right will cause an exponential increase. Those are the correct ways to answer that. Now, that being said, most people are getting their G of S correct. Once in a while, I'll see people putting in extra terms they don't need. In the question, it said simplest, but I think I decided to let it go. And then for lost, I'm thinking you didn't actually answer the question. All right. And then for the FFT ID matching part, it's kind of hard to tell why, but people are just getting it wrong. Which is interesting because that used to, in prior exams, people used to do really well on that. All right. But before we move on to the next part, I'll throw it open to, does anybody have any questions or something you want clarity on?
For question number 3.
Mhm.
Wait, no, question number 3. Yeah. So I wrote out the equation, but I didn't write out the final equation. Is that okay? I say it's wise out phase and stuff, but I didn't actually write out the final transfer function when it's r equal to 0.
You know, I have to look at it.
Okay.
Okay. Because you could, it's possible to write what's happening.
Yeah.
Okay. But
Okay.
I'll take a look. Okay. But again, I try not to just give zeros for it not being exactly in the form I like, although it's nice to have it in a form I can read. But I try, you know, believe it or not, I'm trying not to just take off points if I can help it. Okay. Thank you for your question. Anything else? All right, while you're thinking, I am going to I'm just gonna fix the code here. Okay. So that's pretty good. I think people are all increasing and so part of the thing though is that the exam is cumulative, right? And just before I go any farther, right, these notes are right here in exam solution and you can just click on those. Okay, if you want them, right? So I thought today would be a great time to review midterm 1. Okay. Partly because instead of one of the topics we're going to do is instead of drawing the Bodhi plot, you're given a Bodhi plot and then you have to tell me what the system was. Right. So it's good to review that. And then of course, I think it was question 3 on midterm 1, where is it a low or a high pass? And then you have to do the Bodhi plot and the step response. right? There's other questions there that could be there too, but that's kind of like that's an interview type question, right? That's frequent. So that'll probably be on the final exam. And then the convolution with a plot where you're given a impulse response and some kind of input, right? Square, ramp, something. And then you find the convolution of that, either in the time or the frequency domain method, and then you plot it, right? Now here I've put a link to like my summary of how to plot things, and here's a link to doing simple Bodhi plots, right? I don't think I had a video just on this question, so I didn't have it. But we also have a link to common issues from the last exam, okay? So let's see. Right. So there was question 3, right? Those were the issues. Then there was question 4. And the Bodhi plot was question 2. All right. So any questions before we begin? Okay. So for the Bodhi plot, right, there was really 2 kinds of questions. One where it was a low pass, and one where it was a high pass. All right. And then there was different gain factors, right? And G could have been 1, 10, or 100. And then there were certain relationships between omega 1 and omega 2, right? There's one where omega 1 equals omega 2. Then there's one where omega 1 is less than 100 omega 2. or it could be 10. I have to look up. And then there's one where it's that, and then omega 1 could be 10 or 30, right? So there's 2 choices there times 3 choices times 2 choices times 3 choices. That's how many possible problems, at least of that type, are. All right. So the way I approach these problems is that I look at it and I try to determine what kind of thing it is I'm looking at to begin with, right? And in here, right, I'd see 2 separate numbers that are completely real, right? So I know it's going to be overdamped, which can help a little bit at the Bodie plot, but I'm probably looking for 2 break frequencies, right? And the fact that there's no S here makes it low pass. The fact that this is S squared makes it high pass, right? And then what I just do is, all right, let me set S equal to 0. Well, then I get omega 1 times omega 2. It cancels out with the numerator, and then I'm left with a gain at DC. And then I set S towards infinity, and I can see this is headed towards 0. That's how I know it's low. In this case, when I set S towards infinity, the omega 1 and 2 terms drop out, and then I get S squared divided by S squared. That goes to 1, and then I'm left with the gain, right? And when I let S equals 0, the whole term goes to 0. So that's a high pass. So, you know, in this case, right, I should see, you know, something like that. And in this case, something like that, if we talk about magnitude, right? Now, again, when it comes to phase, I can see that there's, if I multiply this out, the denominator is going to have an S squared in it, right? So it's a second order. So phase is going to change by minus 180 degrees. Now, is it going to start at 0 and go down minus 180? Or is it going to start at 80 and go down to 0, right? We would have to work out. All right. But let's just take this low pass for a second. Let's just say omega 1 equals 1 kiloradian per second. Oops. Right. And omega 2 equals omega 1, and gain equals 10. All right. So again, I let S go to 0, right? I'm just doing this roughly in my head. I'm not finding magnitudes or anything like that. So if this goes to 0, the omega 1s, the omega 2s cancel out, and then I'm left with the gain of 10, right? But I could rewrite this equation and just have omega 1, S plus omega 1 squared, which is what the exam would deliver you, right? You'd see something like 1k squared S plus 1k squared times 10. All right. So that's what you would see. So myself, I do the magnitude, right? I know that something's happening at 1K. All right. And I would just start just drawing in things, by decades, right? So again, if S is now in a Bodhi plot, S omega can't really equal to 0 because it's on a log scale, and neither can the magnitude because that's log. So really it's S much, much less than 1K. So if that happens, then the 1Ks, I'm 10. 20 times log 10 is 20 dB. So I'm going to start at 20 dB, right? And if that was the only thing going on, oops, right? I would just have that 20 dB, right? Now, then the other option is, what about when S is a lot bigger than 1K? Well, if that's true, I'm going to get 1K squared times 10 divided by S squared, which is a line at minus 40 dB. Now you can figure out what that line should be, but you know that it's got to start at 1K, and then it's going to go down so that's 2040, right? If it was first order, it would go down 20 dB per decade, but since it's second order, it's going to do that. Okay. No, Brandon, this is still module 24, where we're actually reviewing midterm 1. It wasn't really in the in Canvas. I sent out an email today that that's what we'd be doing. Okay, so this is just this is a review. Okay, and I'm just doing one of these. All right, now for the phase, right, and again, to do any arbitrary thing, you really want to watch the other video. We don't have enough time to go over every single problem. All right. But really, if you're going to do the phase, there's only one breakpoint, and it's 1K, right? And the important parts are two magnitudes greater and 2 magnitudes smaller, right? Now, let's say you've forgotten the phase part. Well, if I let S to be less than 1K, right, I'm going to get 1K squared divided by 1K times 10. Everything's real. There's no imaginary part. And so the phase is going to start at 0. Right? Then what about, there's only one breakpoint. So to check the other side, right, I have, the magnitude of S really much, much greater than 1K. And so we get 1K S squared times 10. This is all real. So it's 0 degrees of phase. And remembering the trick, this is really something 90 times something 90, which then combines to 180 because it's in the numerator, denominator. When we bring it up into the numerator, it goes to minus 180. So somewhere it's going to be minus 180. Okay. And yeah, this is a bit of a trick, but there's only one breakpoint. So when these two are equal to each other, right, I'm going to get a magnitude with 45 degrees phase times a magnitude with 45 degrees phase. When I bring that into the numerator, it's going to be minus 90. So at 1K, it's going to be minus 90. And then all you have to do is remember your other rules of that. It starts changing at a 10th and it stops changing at 100 times. Oops, sorry, at 10 times. Let me put some better colors here. Right? So now all I have to do is connect the dots. Okay. Now, yeah, when there's two different poles, you're going to see two different frequencies, breakpoints. But in the phase, if they're close enough, you'll still see in the asymptotic version a straight line. But when it's like 1,000 times bigger, that phase will kind of do this option. All right. So start writing this down.
Professor.
Yeah.
So on the final, you're gonna give us the equation, and from the equation, we draw the graph.
Yep. Just, I mean, I'm not saying exactly the same program, but yeah, it's just like number 2 from midterm 1. Okay.
Yeah.
Now maybe the transfer function will be different, right? But so what I want to do now is everybody write this down. Then I want to randomly break you up into groups, and I want you to work on this problem, but now I can't really enforce this, but I want you to give some contact info and make time to meet. I know you're all busy. We're all busy. So just make it for 5 minutes, okay? To talk about 110 or music or parents' taste in music.
Poker.
Yeah. Oh, well, actually, I'm going to have to put that in. It's a good one. I'll come back to that. All right, that's a good suggestion. So, and the thing is, yeah, you're going to be working on 110 and you'll do better. And when you teach somebody something, you learn it better. And sometimes having a peer teach it to you makes you learn better. But in my office hours, I think I'm recognizing that there's a loneliness issue and, not feeling alone. right? Now in the fall, I think we're going to be back in labs and you're going to get to meet people again and, you know, get out and about, even though some lectures will still be online. But trying to feel a personal connection, right? It's important, right? So, but really, I want you to work on this problem. And this is what is known as a formative assessment, where you find out what you know, right? Whereas summative assessment is when I find out what you know, okay? So the thing is if you can do this problem, you know, off the top of your head with no review, which I can't, right? But try to mark down where you think you're having troubles, and now you know where to study. And since we're all short on time, it's better to study on the things that you don't remember than kind of going over the things you're already good at. Okay. So any questions about what we're going to do? I'm going to try to give it 10 minutes. All right. And formative assessment usually means, okay, no points. Okay. But it could be the most important thing, right? But you can come to office hours and we can talk educational theory. Okay. Oh, there's a few questions in chat. Okay, so I'm sorry, I just have to ask. Andrew, I thought you said polka music, not poker, but did I get that wrong? Anyway, you can message me later. Okay. And yeah, Tara, I understand they get stuck in your head. So I actually do try to select something appropriate, just so you know, it's not whatever I happen to be listening to. Okay. So, all right, I'm going to randomly assign you to breakout rooms right now. I'm going to, I have to pause recording though, just so you know. Okay. So sorry, I didn't record properly, but the only thing you missed was a very fun song. And this is the solution to the problem, the Bodhi plot. And I'll just leave it up there a few more seconds, but it will be in the YouTube video. Okay. All righty. No, you cannot find this code on Canvas. Yeah, no, that's my yeah, that's my answer generator. Okay. And no, that's, yeah, one piece of code that is not, you're not going to find there. Normally I'm very generous with my code, not this one in particular though. Okay. But no harm in asking. Okay. So So let's say you saw this problem where R1 equal to R1, and in a way, it doesn't really matter as long as it's a realistic value. And then we can just have RC equals 1. All right. So derive the transfer function. All right. So I recognize, right, that that's inverting, right? And so that's going to be, minus R1 over R1, right, is going to be -1 if everything is working, right? And that means if it's ideal, right? In infinite input resistance, infinite open loop gain, the open loop gain doesn't change with frequency, right? The gain of that stage will be 1. The gain of this stage, right, it's just going to be minus ZC over ZR, which is going to be -1 over RC, right? And so I just recognize that. And so that the total, V out over V in, it's going to be positive, and it's going to be just 1 over, sorry, I missed an S there. 1 over RCS, okay? Which is an integrator, which is out of control. And in a way, the DF2 network takes out of control integrators and turns it into a filter that is in control, right? It's just another way of looking at it. But just because something's out of control doesn't mean that it's not useful, right? Oscillators are useful. And certainly integrators are useful. And even circuits with exponential increase are useful to a point. That's the heart of how a Schmidt trigger works. All right. So that would be V out over V in. Now notice I didn't, start deriving this relationship. Okay. Now, yeah, on an interview, somebody might say using KCL or whatever, derive from basic principles this. But when you start chaining circuits together, right? No, I recognize that gain stage. I recognize that gain stage, right? Now, yeah, and I'll leave it at that because I don't want to run out of time. All right. So in some ways, you might think the Bodhi plot of this it's like tricky, right? Because, well, there's a pole at 0, but Bodhi plots right, because of the logarithmic x-axis don't include 0, so there's no breakpoint, right? But the thing is this S, right, which if we substitute equals j omega, right, it's RC j omega, right? Omega is never greater than anything. It's never compared to anything. It's always active, right? And so, and since 1 over RC is 1, this is really just 1 over j omega, which would equal minus j 1 over omega. So notice there's no comparison. This j is always active. This omega, this real part is always active. And so the phase will always be minus 90, right? And this will always have a 20 dB, minus 20 dB per decade slope, right? So what I have to do is, where is this equal to 0 dB? Well, where omega equals 1, right? Because when omega equals 1, 1 divided by 1 is 1. Log 10 of 1 is 0 dB, okay? So all I have to do is come over here and just kind of draw that line, right? And just say minus 20 BB per decade, right? Now, of course, if we were doing this, if I had asked, where is where is this valid for gain bandwidth open loop gain limitations, right? Well, that's the ideal. And then maybe we'd have this and, it stops working here. And if this is second order, it stops working there. But we're just plotting the ideal. Okay. So now I'm just going to put the phase off here. Right. And like I said, the phase is always minus 90. Yeah, answer generator. I'm just gonna throw it out there, right? Nothing is stopping you from writing your own answer generator in Python. However, you got to show your work, and giving your answer generator away would be considered interactive help. Okay. So now we want the step response of that. So I'm just going to redraw what H of S was mine over S. All right, what's the step response, right? Well, V out step is H of S times a step 1 over S squared. Okay. So now what is V out in time? It's the inverse Laplace of 1 over S, which is T, if you find in the textbook. But remember the plot of T. That's T, right? But remember, this was all started when we multiplied it by a step, which means this should be 0 before time equals 0. So you have to manually add back the U of T, right? Because there's U of T, right? And let me get one like a bigger. And that means, because this is the part you want. All right. Now, yeah, there's no 5 tau. It just keeps going. Like I said, it's an out of control system, but that is a question that could pop up. And there is a my open math question like that. All right. So that's really, one of these questions all in a nutshell.
There's no S squared, Professor, 1 over X squared, the inverse.
I can't quite hear you, Gilbert.
The inverse you find is a 1 over X or 1 over X squared.
Thank you very much. Yeah, thanks. Right, because if you and of course, if you can integrate this constant, right, equal steps in time is going to add equal steps in area, and you're going to get a linear response. So any questions so far?
No, not one right now.
Okay, okay. All right, well, just hold on a second. People are kind of loud in my house today. Okay. So so for this kind of problem, right, the signal input, it can be a step, it can be a ramp, or it can be some kind of combination here, right? And in fact, though, this is really just a linear combination of scaled and delayed ramps, and this is a scaled and delayed combination of step responses. So as you know, you take the complicated thing and break it up into steps, ramps, and deltas, right? And find any common convolutions and then sum those scaled and delayed common convolutions. All right. Now for this kind of question, yeah, there's definitely low pass type impulse responses, high pass impulse responses. I'll give it away right now. For this kind of question, at the time, I hadn't even gone over band or notch pass filter. And so since I'm trying to see what you remember from midterm 1 on the cumulative exam, yeah, honestly, I forgot to take that out of the choice list. But it can't be, all right, because they're actually quite they're actually kind of subtle to look at. And it's okay. But yeah, I know some professors might, have a random type function for any of this, but I try to keep it to where you can kind of do it in your head and then back it up with the math. All right. So if you're, I guess I'm trying to tell you my secret sauce to exam generation. So you could actually generate your own exams and grade yourself, and generating your own questions, your own items. It's actually a pretty good study technique, right? I know one might think, no, I just want to study the problems the professor came up with. Right, but you can see that I have almost a way of generating an infinite number of problems, right? So it might seem like you're not spending your time correctly studying, but really working on these deeper type questions of coming up with an exam question can be better than actually answering, the same one over and over again. All right. But most people seem to get that, the Laplace of G of t times the Laplace of H of t. And if I then take the inverse Laplace of that whole thing, right, will lead to that question. And people pretty much do that pretty well. They don't really have a problem finding a common function and scaling delay. And usually that equation's right. It really boils down to the plot and what's kind of going on. All right. So let's look at Now for a HT of a low pass filter, a real low pass filter, right? It's this. Okay. It's a decaying exponential, right? Because in the complex domain, we have omega naught divided by s plus omega naught, right? And notice this is plus, so this is minus, it's decaying. If this was minus, this would be plus, it'd be exponential increase. All right. So, but what else looks like that shape? Well, that looks like that shape, but it's just inverted. Right? It's just scaling down. What also looks like that shape? Well, things that are longer. Right? Things that are shorter. Okay. But even though this is a triangle, right, it's actually going to have a low pass effect, which it's just kind of going to smooth things, right? It's going to smooth things out. Now, yeah, here's a shape. Let's see. I want x squared and I want that to be 1. That's harder than I want to do today. Okay, but I could have a, something proportional to x squared, where if I had it, basically I'm thinking I have x squared, I can either reverse it or multiply it by a step function. Or I know. Oops. I can have a delayed squared function, multiply it by a rectangle so that I'm only getting right. So this would become this. It's 0 up to that point. Then it decays and then it's 0. So that's how that's what I'm saying is I could get something proportional to x squared. I just have to scale it so that it's doing that. Okay. So that's how you could create another low pass shape. It's just, yeah, for a real continuous time system, you need some kind of RC. It's going to be exponential to K no matter what. All right. So what we're going to do next time, I believe we're going to start system identification, where I give you a Bodhi plot, which can have now complex poles, right? It can be a notch band, low or high, and then you tell me what it was. All right. System identification. But we're going to try to continue this review of midterm 1, right? So that, it's in our heads for a lot longer. All right. And yeah, I want to do more breakout sessions. I'm going to try to do one every day. or every class period until we're done. Okay. Any questions?
No, not yet.
All right, I'm going to stop recording then.